Pluto is a great distance from the Sun, making it about 1,500 times dimmer than the Sun appears from Earth. This immense distance results in extremely cold temperatures, dropping to approximately -230 degrees Celsius during the night. In rare heat waves, temperatures might reach as high as -170 degrees Celsius. Pluto also has a very thin atmosphere. Welcome, curious minds, to an exploration beyond the familiar realms of our solar system. What if I told you that Pluto, the distant and mysterious dwarf planet, is potentially on a collision course with Neptune, the ice giant? Pluto's rebellious nature has been apparent since the beginning, a renegade on the fringes of our celestial neighborhood. Its orbit daringly crosses paths with another planet, challenging the conventional norms of planetary behavior. Such conduct is unusual for a planet, indeed. From the complex intricacies of Pluto's orbit to the concerns raised by astrophysical luminaries like Neil deGrasse Tyson and Michio Kaku, a lingering question persists. Will these celestial giants end up colliding? Could the convergence of their paths result in unforeseen consequences for Earth? Today, we embark on an introduction to a cosmic journey filled with uncertainty. While the answers to these celestial queries may currently elude us, the potential for a collision of such cosmic magnitude serves as a stark reminder that the universe is a stage for both inspiring and potentially terrifying events. Join us as we delve into the mysteries orbiting our understanding of Pluto and Neptune, contemplating the possibilities of a celestial clash that could reshape the cosmic balance of our solar system. The stage is set, and the unfolding drama beckons us to witness the enigmatic dance of the planets. Among other potential space disasters, the cosmos harbors an array of enigmas, including the intricate puzzle known as the three-body problem. Scientists anticipate other potential cataclysms within the celestial theater. Although a planet colliding with another in space is highly unlikely, it is not entirely out of the question. Gravitational interactions, as described by the three-body problem, affect planetary orbits. An example of a space system where gravitational forces produce a periodic pattern known as orbital resonances is TRAPPIST-1, which has 7 planets roughly the size of Earth. Over time, these patterns might weaken planetary orbits, increasing the likelihood of collisions. Currently, no collisions are taking place, even though systems like TRAPPIST-1 are very dense, and planets impact each other's orbits, particularly when they are close. Scientists regularly monitor these systems to understand their dynamics better. This information enhances our understanding of how planets move through space. Another intriguing factor is rogue planets, which drift aimlessly through space rather than orbiting a star. Expulsion of planets from star systems can occur due to gravitational interactions or other astronomical phenomena, such as a close approach of another star or dynamic instability in systems with multiple planets. Over time, these rogue planets can travel great distances, potentially reaching regions far from their original locations. They might even cross paths with other star systems on their solitary journeys. The possibility of a rogue planet colliding with another planet increases if one of these planets travels into a new solar system. Nevertheless, a rogue planet striking another planet head-on is quite improbable due to the vastness and largely empty nature of space. The sparsity of planets in open space and the immense interstellar distances discourage frequent collisions. While the likelihood of 2 rogue planets colliding is already low, the frequency of rogue planets is much less compared to stable stars and planets. In the event of a galactic merger, the involved star systems can become chaotic. However, it is highly improbable that planets will collide head-on during these cosmic events due to the vast interstellar distances. The orbits of stars and planets in emerging galaxies are significantly altered by strong gravitational forces, potentially causing a planet to become a renegade world, expelled into the cold, black depths of intergalactic space. Conversely, gravitational disturbances could expel planets from their orbits, causing collisions with one another or even with their host stars. When gas and dust are compressed under extreme pressure, gravitational rearrangement can lead to the formation of new celestial bodies or the emergence of stars. In our solar system, the late heavy bombardment suggests that around 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This surge in impacts is believed to have resulted from gravitational disturbances caused by the outer planets. During this chaotic phase, gas giants like Jupiter and Saturn underwent migration, disrupting the orbits of numerous smaller bodies in the Kuiper belt and asteroid belt. Consequently, these smaller objects were thrown into unpredictable paths, with many entering the inner solar system. This influx led to a significant increase in impacts on terrestrial planets, including Earth. While these collisions did not involve direct clashes between planets, they illustrate how gravitational interactions can cause substantial changes in the trajectories of celestial bodies. This bombardment is thought to have played a crucial role in shaping the surfaces and geological histories of planets in our solar system. Additionally, it may have contributed to the delivery of water and organic materials to Earth, influencing our planet's development over an extended period. As stars go through changes in mass, their planets can wind up in different orbits or even cross paths. This is particularly noticeable in systems where stars are at the end of their life cycle. As a star ages and consumes its nuclear fuel, it often undergoes significant mass changes, especially during stages like the red giant phase or when it sheds material in a planetary nebula. These variations in stellar mass can significantly impact the gravitational balance of the system, causing the orbits of nearby planets to either move outward or become more compressed. This phenomenon is more likely to occur in multi-star systems, where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, exacerbating orbital shifts and increasing the chances of orbits intersecting. This can result in scenarios where planets might be captured by another star, collide with other celestial bodies, or even get ejected into interstellar space. Pluto's unique orbit, initially recognized as a full-fledged planet, was eventually reclassified as a dwarf planet due to its distinctive orbit. The astrophysical community remains captivated by Pluto, finding it fascinating despite this reclassification. However, there are concerns regarding Pluto's proximity to Neptune's orbit. According to recent forecasts by prominent scientists like Neil deGrasse Tyson and Michio Kaku, there is an alarming possibility of a collision between Pluto and Neptune. Pluto's orbit around the Sun is unique. It has not completed a full revolution since its discovery in 1930, and its orbit spans an extended 248 years. The significant deviation from the roughly circular orbits of the major planets makes Pluto's course highly elliptical, adding to its intrigue. Pluto's orbit is also steeper than the other planets, with an inclination of 17 to 28 degrees relative to the ecliptic plane. The combination of its elliptical shape and inclination adds complexity to Pluto's orbital pattern. A notable feature is where Pluto's orbit intersects Neptune's orbit. For about 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their positions in the solar system. This raises the question: why hasn't a collision between Pluto and Neptune occurred? The explanation lies in the gravitational influences exerted by other planets. The examination of Pluto's orbit began shortly after its discovery, revealing a puzzling trajectory for astronomers. Unlike most planets with orbits close to the ecliptic plane, Pluto has a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's orbit. The three-body problem, which involves understanding the motion and gravitational interactions of three celestial bodies, Pluto, Neptune, and the Sun, is a key aspect of this puzzle. Predicting their trajectories from their starting positions and the effects of gravity on each other is complex. For Pluto, terms such as libration, latitude libration, and the VZK oscillation help solve this astronomical mystery. Astrophysicists consider libration crucial as it maintains planetary orbits. When Pluto crosses Neptune's orbit, it is at least 90 degrees away, a critical distance that prevents collisions. Latitude libration, which refers to the vertical movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it remains significantly above their orbital plane, providing additional protection against collisions. A key factor in understanding celestial motion is the VZK oscillation, named after the scientists Van Leeuwen and Kai, who explored gravitational interactions between three space objects like Pluto, Neptune, and the Sun. The VZK Oscillation explains why Pluto's orbit appears unusual, but remains stable over time despite apparent randomness. Underlying patterns and rules maintain order in space. These factors collectively stabilize Pluto's orbit, preventing collisions with Neptune or deviations from its path. The three-body problem helps us understand how the gravitational influences of these space objects affect their trajectories. Studying this contributes to our knowledge of Pluto, our solar system, and distant celestial bodies. Numerical simulations in the late 1980s revealed that, despite its stable properties, Pluto's orbit is technically chaotic, with minor initial deviations leading to significant differences over millions of years. Nonetheless, Pluto's extraordinary orbit exhibits remarkable stability over long periods, effectively mitigating potential chaos. Recent computer simulations have deepened our understanding of the intricate dynamics involving large planets like Neptune, Jupiter, and Saturn, influencing Pluto's trajectory around the Sun. Neptune's distinct gravitational influence, completing 3 orbits for every 2 of Pluto's, significantly contributes to the stability of Pluto's orbital path. Jupiter's gravity also plays a role, though less significant than Saturn's. Collectively, these observations demonstrate that Pluto is in secure and steady motion across space over billions of years. This stability is guaranteed by the combined influence of Jupiter, Saturn, and Neptune, which keeps the motions of celestial bodies in the universe ordered and predictable. Without these systems, the solar system would be more chaotic and unpredictable, increasing the likelihood of collisions and ejections from otherwise stable courses, potentially having far-reaching consequences for other celestial bodies. In light of recent speculation about a possible collision between Pluto and Neptune, it is essential to understand Pluto's orbit. This knowledge helps us better grasp the ever-changing nature of the solar system. The case of Pluto illustrates how the complex interaction between orbital mechanics and gravitational forces can bring apparently unstable orbits into equilibrium. To better understand our place in the universe, continuous observation and analysis of these events are crucial. Space exploration frequently reveals the erratic behavior of celestial bodies, with Pluto's orbit serving as a classic example of orbital chaos. This concept shows how a celestial body's trajectory is highly dependent on its starting point, with minor shifts in location or speed significantly impacting its path over time. Scientists' understanding of Pluto's motion in space is largely due to computer simulations, which use intricate mathematical models to simulate the gravitational interactions between Pluto and other planetary bodies like Neptune. These simulations illustrate how tiny changes can have substantial effects on Pluto's trajectory. The models uncovered fascinating aspects of Pluto's path in the late 1980s. Despite being stabilized by features like libration and latitude libration, Pluto's orbit remains somewhat unpredictable. Minor deviations in Pluto's position or velocity can lead to significant changes in its course over several years. Even though Pluto's orbit is inherently chaotic, it remains stable for long periods, suggesting that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows a structured order. Predicting cosmic events, especially for planets with unpredictable orbits like Pluto, is challenging due to the inherent unpredictability of these systems. Numerical simulations help us understand and anticipate the future paths of celestial bodies, but also reveal the limits of our predictive abilities. These models depend heavily on accurate initial conditions and complex interactions, with even small errors potentially leading to significantly different outcomes. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational influences of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system, demonstrating how each planet's presence and position can impact the stability and trajectory of other bodies in the system. Concerns about a potential collision between Pluto and Neptune, while intriguing, are largely unfounded based on our current understanding of celestial mechanics. The stability of Pluto's orbit, governed by complex gravitational interactions with other planets, ensures that such an event is highly unlikely. In conclusion, the dance of celestial bodies in our solar system, including Pluto and Neptune, is governed by intricate gravitational forces and orbital dynamics. While the possibility of a collision between these distant planets sparks curiosity and speculation, the fundamental stability of their orbits, upheld by the laws of physics, mitigates such concerns. Through ongoing observation, analysis, and numerical simulations, scientists continue to deepen their understanding of Pluto's unique journey through space, shedding light on the broader mysteries of our dynamic universe.